Hello? Oh, hi. My name's Steven. This is a joint work with an amazing set of co-authors, Rachel Cummings, Katrina, Ligett, Kobbi, Nissim, and my advisor, Aaron Roth. Okay, so since we just had our lunch break, let's start with something not so technical by telling you a story about my friend whose name is Data Scientist. He works at the tech startup firm, and his day-to-day job is to use machine learning algorithms to train on data set to produce classifier to do prediction task. Okay, so his daily routine basically start with downloading state-of-the-art machine learning algorithm, applying on the data set, which gets some result, and the result usually is not very good. The error is usually pretty high in the beginning, but then he observed the outcome, think about it pretty hard, tune the parameter, try it on the data set again, and time again, he can keep doing it all day long and then keep driving the empirical error to smaller and smaller. And about 1,000 iterations later, he found the best classifier among all of these trivial with really, really small classification error on the data set. Now, he's a little worried because over this 1,000 iterations over the data set, the data is so heavily reused. Even when he started out with the holdout set, the holdout set was used multiple times. So he wanted to think about how good the classifier is at the end when it's used on the freshly drawn data. Okay, so the problem gets even worse when there's someone else in the company that's not the data scientist. They're called the Marketing Analyst. What they're doing is, they will look at the data scientist's report and think very hard about it and try to come up with business strategy by deriving insights. Okay, so in this case, he's trying to digging up some really idiosyncrasy about the data set and come to a very interesting, surprising conclusion that all teenagers love Justin Bieber. Just when he was about to recommend to the firm to use this claim to use Justin Bieber as an icon for targeting teenager users, he was worried whether such a claim actually generalized over the population or the underlying distribution. So it's clear that the problem I'm trying to get to is overfitting, okay? And while this corporate example might seem contrived, actually overfitting is a real concern even in our scientific community, okay? So the real problem here is actually the adaptivity when we're conducting scientific experiments, okay? Because the way we choose our scientific experiment often depend on what has previously done by other scientists, and we use the same data to derive our scientific results. Overfitting is sometimes unavoidable, okay? So the problem of preventing overfitting or false discovery is a decades-old subject in machine learning and statistics, but what is really missing in the traditional framework, okay? So let's take a look. Usually we'll be starting with a pre-specified algorithm. There is a procedure that's determined before we even see the data. And then we apply the algorithm on the data set, which generates some output, okay? So by using standard technique, we can bound the generalization error. That is, we can bound the empirical error, bound difference between the empirical error and the true error, okay? Unfortunately, that's usually not the end of the story, right? So by observing the output, sometimes we might actually want to reuse the data or revise the method to run on the data again so we can maybe arrive at a better model and improve the outcome, okay? But some of this is not allowed in the traditional static data analysis task, right? So this traditional generalization guarantee doesn't hold if we decide to reuse the data again, okay? So part of our goal in the paper is to formalize a generalization notion specific to adaptive data analysis, okay? If you think about the examples I just told you, you can distill from it two desired properties that you want to have for such a generalization notion, okay? The first and the most important one is I want robustness to arbitrary post-processing. Meaning, if I run the algorithm and produce some output, I do not want the subsequent analysis, tailored to this output to be overfitting on the data set I'm using, okay? The second one I want to have is composition. So when I design a class of algorithms that satisfy this generalization guarantee, I want them to compose and continue to have this generalization property, okay? So this way, I can do some form of exploratory data analysis and keep using the data iteratively. So I can improve the model while still be able to argue how good the model actually is on fresh samples. Okay? So how do we formalize such a generalization guarantee? Okay, so important tool here we'll be using is the statistical queries. Okay, so I want to use this type of queries to capture a large class of data analysis task. To set up some notation, there will be a data universe X. Okay, this is the universe of all possible examples, and there will be an underlying target unknown distribution over the examples. And a data set is a multi-set from the universe consisting of n points, sample IID from the underlying distribution. Okay, a statistical query is defined by a predicate, which is a mapping from the universe element to a real value between 0 and 1. Okay, so you can talk about the expected value of a query, which is like the expected predicate value over a random draw from the distribution. Okay, and you can also talk about the empirical average of the predicate, which is the average predicate values evaluated on the data set. Now, there's a very natural way to talk about overfitting using this language. Okay, so I'm going to say a predicate Q overfits a data set if the empirical average and the expected value, the value of the query, are very different. Okay, meaning the data set I'm using is no longer representative for the query I'm trying to think about. Okay, and we want to avoid this kind of phenomena. Okay. So there are some advantages of using this type of queries to capture the type of data analysis we want to run. It's pretty general, and when you think about it, the risk and the error function of an output hypothesis can be formulated as a SQ query. And if you care about computation, the gradient of the risk function can also be formulated as such query. And finally, if you think about packed learnable classes, almost all packed learnable classes, except for some classes like parity function, can be learned using access just to this kind of SQ queries. Okay, so I want to formalize a notion for preventing overfitting by statistical queries. Okay, so I want to adopt an adversary point of view. Okay, let's start by running an algorithm on a data set. Okay, and the algorithm will output some stuff, and let's introduce an adversary who get to observe the output. And then the adversary can actually do arbitrary post-processing on the output, okay? And he can even be computationally unbounded, okay? Now the adversary will output some statistical query, Q, and our goal is to, formalize some notion for the algorithm such that just by looking at the output, the adversary would not be able to come up with the overfitting query, right? So this notion will formalize it as robust generalization, and more formally, an algorithm satisfies epsilon delta robust generalization if for any adversary there is a mapping from the output to a query. Such query would not overfit the data set the algorithm is performing the computation on. Okay, so here the difference between the empirical average and the expected value is no more than epsilon. So you can think of the epsilon as the accuracy parameter, and I want this to hold with high probability 1 minus delta, so with the delta being a confidence parameter. Okay? Any question about this definition? All right. So what kind of algorithm satisfy this robust generalization guarantee? Even though we are the first one to pose this notion, actually this guarantee is studied before, notably by 2 sets of authors. The first one by Dwork, Feldman, Hart, Pitasi, Weingold, and Roth in 2015. There were 3 papers, one of them in Science, and more recent one by Basili, Nissim, Steinke, Smith, Stemmer, and Ullman in Stock 16. They show that there are basically 2 classes of algorithms that satisfy this guarantee. The first one is the class of algorithms that satisfy differential privacy. Okay, they show that using algorithmic stability of differential privacy, you can guarantee robust generalization. And the other class is simpler. Any algorithms with small output space also guarantee robust generalization. Okay. Here, the proof is simpler. You can basically use the OCAM style of Newton bound to get such a guarantee. So in our paper, we basically derive a new class of algorithms for robust generalization called compression schemes, which allow us to solve some problems that is not previously known how to solve under these previous two types of algorithms. And I realized time is about up, and I have half of the paper I haven't talked about, but I want to end with advertisement, which is my co-author Rachel and I will be on the job market next year, and you can see that we do fun scientific research, so let us know if there are any hiring positions. Thank you.